let me close that door and let me show some things to you. So, this is an issue we ran into with our aldehyde sugar. I knew I couldn't remember that it was a sugar while I was doing it, but I can look at the structure of all these sugars to show you what I was trying to say. These when we're talking about things that aren't chiral centers, right? We have 3 chiral centers, right? In our ribose, right? So you couldn't figure out the other 2, like you could get 6, but what I meant by alternating is we have this D ribose in the in your example. You have this D ribose. You can take one and flip it over, so that is D arabinose, right? You can take another one and flip it over. That's D lioxose, and you can take another one and flip it over. That's L ribose. But the same is true for L ribose. You can take one L ribose and flip it over, and then you get one from L ribose and flip it over, and then you get L xylose. You can take another one from L ribose, and then you get what would that be? It'd be D-arabinose, and we can do alternating patterns. These alternating patterns in this 5-carbon aldehyde sugar, we can see that this is all 8 conformations. These non-chiral centers, because they're non-chiral, they don't rotate, but these chiral centers can rotate. But that's why it's easier if we just use the 2 to the power of n, because each chiral center can have 2 positions. It would be each chiral center can have 2 positions, right? So, like let's say we're doing this like as a logic function. We have 3 2s. Well, you can do this binary wise, right? It can either be a 1 or a 0. 1 or 0, 1 or 0. Right? There's a state where it's all 1s. There's a state where it's all 0s. There's a state where it's 1, 0. I need a bit more bits. I need a few more bits than this. I'd need about 8 bits to do this binary wise. But okay, yeah. So there's a bit where they're all on. There's a bit where they're all off. There's a bit where 1's on. There's a bit where 2 are on. There's a bit where the first one's off, this one's on, this one's on. There's a bit where these 2 are off. There's a bit where the one in the middle is on, those 2 are off. And that's 1, 2, 3, 4, 5, 6. I'm missing 1 at, let's see, boop, boop. 2. And then, oh, wow, there's one where the one in the middle is off, that's on. It's easier when you do it like that in binary. But you can see here how we get all 8 of our possible conformations by using this binary bit system. That's why I'm like, it's a bit more complicated, and it's easier if you look at it like this rather than looking at the overall structure that you're working with. So that's why we had a lot of issues with that. I was trying to explain it from a bit more of a simple perspective, but I was like, I can just do this binary wise, and it'll be a bit faster. But just something to remember is when you're working with these don't rotate. That's what I said it pretty bad, so these don't rotate. That's why I was like, my explanation is really bad in the lesson. These stay constant. This has to rotate. But fundamentally, when this is rotating, this is also moving, but it's not its position on the central carbon chain is not changing. So now let me check something real quick. I'm gonna pause. Okay. It's recording again? Okay, now we're back at it. So, like I was saying earlier, there's rules to assigning priority. Alright, and those are called Kahn-Ingold priority rules. You can see them here. It's first you look the atomic numbers of each atom. If there's a tie in atomic number, then you look at what's a bond later. And then if there's still a tie, you must continue until the tie is broken. And if the tie isn't broken, that means it's an H or a molecule. So, this is a simple case. This will be a CH3. This carbon in the center has a bromine, an OH group, a hydrogen, and a carbon with bonded to a few hydrogens. Number 1 is bromine because it has the highest atomic number here, and this is kind of why I went with kind of why I see it as electronegativity. But if you were comparing bromine and fluorine, which both can be in an organic molecule, that would start to fall apart because fluorine's more electronegative than bromine. But it's based on atomic number. Now that's 1. Oxygen's next. That's 2. Carbon's 3. And hydrogen is 4. Now we're trying to go in order, so 1 to 2, 2 to 3, and then 4. So we're going counterclockwise, which is S. Sinster, right? Now it would be S, but what did I say about if the lowest priority is on the wedge coming forward? It's not correct. You do not want the lowest priority on the wedge. The lowest priority has to be facing away from you. Especially if there's a higher priority facing away from you currently. So to fix that, we flip it 180 degrees. So it becomes OH on the wedge. Boom, 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 boom. H on this. It's flipped. So bromine's here. This, then we go to our CH3, and that is clockwise, so now it's R. So whatever you calculate as your S or R, we go based on we then flip it if the lowest priority is on this this wedge. Okay? So, as far as pre-log rules, the first one is atomic number. Priority is assigned to the atomic number. Atomic number. Number 2, if there's a tie, look at the second atom. Tie, second atom. Okay. Let me just... So if there's a tie, second atom. Okay. I'm not right-handed, so it's even harder for me to write with the mouse. But what that means is like... Okay, let's go back to board 2. Actually, let me open up a new board. Board 4. If we have carbon, this is the wedge. OH, dotted line. Hydrogen. And then, this is another carbon. These are both carbons. But this one is carbon bonded to OH. This one is carbon bonded to 3 H's. How we'd assign priority in this case would be we go OH, oxygen's more has more is more higher atomic number than either two, and it's always higher than hydrogen. Then we go carbon. Well, carbon has carbon and carbon are tied. Well, what's the next one? The atomic number of the next one. Oxygen has a higher atomic number than hydrogen. So this is number 2, this is number 3, you're number 4. This is on a wedge back, so we don't have to alter the rotation. It's going this direction, That's clockwise, R. So that's rule 2. If there's a tie, second atom. And then rule 3, if there's still a tie, continue. If tied, continue. So let's go back here. Okay. This isn't CH3. This is CH2. And it's bonded to. I know this is gonna look horrible, but it's bonded to an OH right here. Well, this is CH2. This is carbon. This is CH. This is CH2 as well. And it's not bonded to an OH, it's bonded to a, not an H2O, it's bonded to a CH3. Well, now we look. Boom. These carbons are the same. These carbons are the same again. Oh wait, I need to add another carbon. This is bonded to a CH. This is a CH2. This is also a CH2. This, and it's now it's a CH3. And this is a CH2, and that's bonded to an OH, finally. Well, we go. The carbons are the same. They're both CH2. This carbon's the same. It's also a CH2. This carbon has an OH. This carbon has a, what do you call it? This carbon has an OH. This carbon has a CH3. So, this one's higher priority now. It's 2. That's 3. This is still on the back. So it's 1, 2, 3. Now, in this case, this is a Sinster carbon because it's going counterclockwise. And I hope that helps. That's how you use the pre-log rules. So you flip 180 degrees when the what do you call it? When the lowest priority is on the projecting the wedge. When the lowest priority is on the wedge, you flip it, and then that flips your rotation. So it turns it from S to R right here. And when you're doing priority, if there's a tie, you keep going, and if you never break the tie, it's not a chiral molecule. It is a chiral. It is a chiral. If you never break the tie. And that's that. I hope that helps. Next time we talk, I'll hopefully be a little bit more prepared, but it's been a while since I've done organic chemistry, so I had to look at my notes. But, ciao.